Welcome everyone and thank you for joining us for our expert sessions. These are short webinars that take place every week and last no more than 30 minutes, bringing you valuable insights from the industry experts. Today's session will be presented by Sonny Solanki, who's Senior Technical Manager at I-Gard. Sonny is an electrical engineer by McMaster University with 8 years of experience in protection systems and relays. Through his career, he has educated consultants and end users on the benefits of integrating electrical protection products into their design to enhance personnel and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high-resistance grounded systems, low-resistance grounded systems, hybrid HRG systems, ground fault and arc flash protection systems, and resistor-based solutions and personal protection products. We are excited to have him today, and we appreciate your participation. Thank you, Sonny, for your time.
Thank you for the introduction. My name is Sonny. Today's topic is going to be system grounding techniques and the role of resistance grounding in industry standards. So we'll start off with what is a ground fault and why ground faults matter. So a ground fault is an unwanted connection between the system conductors and ground. And if it goes unnoticed, it can cause havoc on plant production processes, shutting down power and damaging equipment, leading to hours or even days of lost productivity. It can also lead to safety hazards such as fire and electrical shock, and it can usually occur due to loose connections, worn wire insulation, exposure to moisture, or any external natural condition. Now, in the Industrial Power System Grounding Design Handbook, it indicates that 95% of electrical failures begin as a single phase to ground fault, with the remaining 5% consisting of 4% being phase-to-phase failures and 1% being three-phase failures. So with high resistance grounding, what we're looking to do is take care of 95% of the case with the phase to ground fault and limiting that fault current to a specific value. But let's look at what the industry has been using in the past and see how we can get to the advantages of utilizing high resistance grounding. So first, we'll take a look at ungrounded systems. Ungrounded systems were utilized a lot in the process industry in the past due to its capability of maintaining process continuity in the event of the first line to ground fault. If phase C gets faulted, phases A and B elevate to a higher voltage to cover the loss of phase C and maintain the line-to-line voltage. It offers a low value of current flow for line-to-line ground faults, and it has a low probability of escalating into a phase-to-phase or three-phase failure. The issue with ungrounded systems, though, is that because there's no line-to-ground reference, it is very difficult to locate a fault in this type of system. There's no ground return path for fault current to flow back and be picked up via zero-sequence current sensors. That path that the ground fault actually takes is through the distributed capacitance that exists between the conductors and ground. As a result, this type of system has difficulty locating faults and is also susceptible to transient overvoltages, which can occur on the unfaulted phases when a ground fault is occurring. So these transient overvoltages can cause punctures in insulation and also impact the life cycle of your electrical equipment. A second ground fault on another phase will result in a phase-to-phase short circuit causing damage to equipment, and code requires an ungrounded system to be equipped with a ground detection device. So this is usually a 3-light system that is connected between each of the phases to ground. If one of the lights goes out, you know that that is the phase that is impacted with ground fault. Now, in the IEEE standards, they have a few references in relation to ungrounded systems. The overvoltages associated with ungrounded operation reduce the useful life of insulation so that electrical circuits and machine failures occur more frequently than they do on grounded power systems. And these overvoltages, which can be several times normal in magnitude, result from a resonant condition being established between the inductive reactance of the system and the distributed capacitance to ground. Further to this transient overvoltage could be as high as 6 or 8 times your phase voltage, and that overvoltage can puncture insulation and result in additional ground faults in the system, which is unwanted. Now, in the commercial and residential space, we have a lot of solidly grounded systems, and in industrial applications, we have about 60 to 70% of the cases being solidly grounded. In a solidly grounded configuration, you would typically have a delta Y transformer where the neutral is solidly grounded, and this solid ground connection between neutral to ground controls the transient overvoltage condition by shorting the capacitance that exists between the conductors and ground. In addition addition to that, this system ground establishes a ground return path for fault current to easily be located based on zero sequence current sensors. In addition to that, this solidly grounded system is able to satisfy single phase loads with the distribution of the neutral for a 3-phase 4-wire system. The issues with solidly grounded systems is that there's high values of fault current that can flow back to the source, back to the point of fault, which could create an arcing effect and can cause severe equipment damage during fault conditions. Sustained arcing faults can release intense heat and mechanical energy, causing severe damage and injury. And there's a very high likelihood to escalate from a single phase fault to a phase-to-phase or a 3-phase fault in this type of system. In addition to that, we can't achieve process continuity with the solidly grounded system because we have to trip immediately on first fault due to the high value of fault current capable in this type of system. So we have to trip within a second or less with a prospective ground fault trip setting of 1200 amps or less according to section 14 of the code. Now, for solidly grounded systems, if we look at the IEEE standards, it indicates that solidly grounded systems have the highest probability of escalating into a phase-to-phase or 3-phase arcing fault, particularly for 480 and 600 volt systems. The danger of sustained arcing for phase-to-ground fault probability is also high for 480 and 600 volt systems, and a safety hazard exists for solidly grounded systems from the severe flash, arc burning, and blast hazard from any phase-to-ground fault. Further to this, on the right, it indicates the high magnitude of destructive arcing ground fault currents that can occur on a solidly grounded system. So with resistance grounding, what we're looking to do is try and take a few of the advantages of both of the systems we mentioned previously for ungrounded and solidly grounded systems and make the system more safe and more operational. So for resistance grounded systems, it involves adding an impedance between the transformer neutral and ground. This keeps the ground fault current at a low level, preventing the buildup of sufficient energy for arcing and making the system safer to operate. So it's typically used in low voltage and medium voltage systems to limit the ground fault current. We're placing this resistor between the XO point and ground, which is in series with the ground return path of the system. And as a result, we can clamp the current to a specific value. There's no arcing ground faults as with solidly grounded systems, and we're controlling the transient overvoltage condition by sizing this resistor in accordance to the capacitance in the system. Now, in the IEEE standards, the reasons for limiting the current by resistance grounding is to reduce the electrical and mechanical stresses on equipment, also to reduce the electrical shock hazards, and to reduce the arc blast or flash hazards to any personnel who may be close by in case a ground fault occurs. In the middle section, it talks about how high resistance grounding provides the same advantages as ungrounded systems, yet controls that severe transient overvoltage we were talking about. So basically, high resistance grounding has the same benefits as an ungrounded system, except without the severe transient overvoltage. High resistance grounding helps ensure a known magnitude for ground fault current. So if I have a 5 amp NGR situated at my source and I have 3 amps flowing through it, that would be a 60% fault, we can say, which isn't something that we can really do for ungrounded or solidly grounded systems in terms of quantifying the fault and the percentage of the fault. So that's very advantageous as well for consultants and end users who are designing systems. Now, in this example where we have a 480 volt 3-phase 3-wire system, we've connected NGR between the neutral point and ground in an effort to limit fault current to 5 amps using a 55.4 ohm resistor. At the moment, the system's in normal operation with the line to ground voltages at 277 volts, and we have 0 volts and 0 amps at the neutral. I've drawn out the capacitance that exists between the conductors and ground. These capacitances don't provide any contribution at the moment in normal operation because as they go to ground, they're canceling each other out based on their vector. Our vector diagram for voltage is also intact, and our line to ground voltages are in normal condition at the moment. Now, when a fault occurs on phase A, the phase A fault current will flow through the resistor to be limited to 5 amps, head to the neutral point, up through the A phase, and down to the point of fault because current is trying to close the loop in this scenario. In addition, you also notice that the ground fault here is shorting out the capacitance that exists on phase A. Thus, some current will flow into B and C capacitance, causing their voltage voltage to elevate to 480 volts line to ground. This allows us to maintain the voltage between the phases at 480 volts to continue supplying power even when this ground fault is still in the system and being limited by this NGR for an indefinite period of time. The NGR is continuous rated, so it can withstand this 5 amps continuously, and you'll see that the neutral also elevates to the line to neutral voltage of the system because we need to have a voltage drop across the resistor for the current to flow. So we have basically shown you what happens during a ground fault scenario and how we are able to achieve process continuity in the event of the first phase to ground fault. So we're not tripping the faulted feeder. All the unfaulted feeders are still operating based on the voltage present for the system, and this is how we're achieving that process continuity. Now, NFPA 70E has 2 annexes. In Annex 0.2.2, it says that design option decisions should facilitate the ability to eliminate hazards or reduce risk by doing the following: reducing the likelihood of exposure, reducing the magnitude or severity of exposure, and establishing an electrically safe work condition. Further to this, in Annex 0.2.3, they list out different incident energy reduction methods that can be utilized to reduce the magnitude or likelihood of an arc flash incident. High resistance grounding is actually the only one out of the incident energy reduction methods listed that is reducing the likelihood of exposure. By placing a resistor in the ground return path that would limit 10 amps or less on a 5 kV or less system, you leave insufficient fault energy and thereby help reduce the arc flash hazard level. The only issue with high resistance grounding is that it's not able to reduce the magnitude for phase-to-phase and 3-phase faults. For a phase-to-phase failure, if you think about it, the 2 faulted points would just circulate current between each other, while the NGR that's sitting at the source is not going to see any of that current. Same thing with the 3-phase fault. The NGR is essentially bypassed because the current is just circulating between the faulted points. As a result, the instantaneous function of your breaker should be picking this up and tripping the system open. But at least high resistance grounding is handling 95% of the cases in which you're experiencing a single phase to ground fault. So far what we've concluded is that high resistance grounding is able to take the advantages of ungrounded and solidly grounded systems while mitigating majority of the disadvantages associated with this system. And that's why we're seeing more and more consultants and end users implementing resistance grounded systems in their designs to maintain high operational availability as well as provide a high level of safety for equipment and personnel. Now let's take a look at how we can locate a ground fault in a high resistance grounded system. So in this example here, we have a 3-phase 3-wire system where 3 motors are connected. We've placed a resistor between the XO point and ground in an effort to limit fault current to a specific value. Now, if motor 3 phase C is experiencing a ground fault, this ground fault current is going to flow back through this resistor. We're going to see neutral voltage elevation, and we're going to indicate to the operator that we have detected a ground fault. The next step for the operator is to locate the position of the ground fault, and he can activate this feature called pulsing on our touchscreen display. Pulsing will control this contactor to open and close at a frequency of 1 Hertz. This contactor is hooked up to a wire, which is shorting out half the resistance. And when you short out half the resistance, you're doubling the current. So we're essentially creating a current signature, which would be a back and forth movement, and that takes the path back to the point of fault. So we're looking for the back and forth movement using a Rogowski coil hooked up to a multimeter. We check motor 1 and motor 2. We don't see any back and forth movement. We check the MCC terminals for motor 3, and we see the back and forth movement. And then we continue our path downstream to the motor terminals where we're not seeing back and forth movement. So we can rule out that motor 3 is still healthy. It must be the pathway between the MCC and the motor, which is experiencing the fault, which is typically the cabling in this case. So this is a very effective way detecting and locating a fault while the entire system is still energized. We haven't de-energized anything, so there's no downtime, and then they can have a planned outage to address this first ground fault. It's always important to address these ground faults and just not hold the first fault in the system for an indefinite period of time, because the possibility of a second fault occurring on another feeder on another phase could create a phase-to-phase failure, which is unwanted. So in your standard operating procedures, it's highly recommended that you provide corrective action as soon as you possibly can on your next outage or within a shorter duration. Now let's take a look at the case studies. So here we have one from a pulp and paper mill. In this case, we converted their system from solidly grounded to high resistance grounded. This case study presents a situation where we replaced 100 solidly grounded systems for high resistance grounded systems to reduce arc flash risk and improve safety and reliability. So high resistance grounding was installed to reduce the probability of phase to ground faults escalating. Additional arc flash mitigation included digital relays, maintenance mode switchers, and upgraded CTs with faster fuses as well. The findings was that HRG increased incident energy in some cases, but reduced fault occurrence. Motor failures and repair costs decreased significantly, and operational continuity improved due to being able to hold the fault in the system and continue operation. While HRG alone may increase incident energy, when combined with other mitigation techniques, it effectively enhanced the safety and reliability of this pulp and paper mill. And we have this paper available for you to view, so that will be available after this presentation. So we could see that the conversion from solidly grounded to HRG included the following benefits: continuity of operation, ability to easily locate the ground fault while the system is energized. We controlled the transient overvoltage and reduced damage on equipment by limiting ground fault to low levels, and we significantly reduced the arc flash risk. Our next case study will explore a conversion from an ungrounded system to high resistance grounding. So this case study presents a situation from a plastics and packaging facility that upgraded its aging ungrounded electrical system to a high resistance grounded system with pulsing technology to reduce arc flash risk and improve fault detection. So this plastic and packaging facility was dealing with some transient overvoltages and difficulty in locating faults. We assessed their existing 600-volt ungrounded system and its limitations. Then we established a neutral with the connection of a zigzag grounding transformer to their three phases, and we placed an NGR from that artificial neutral to ground to convert that system from ungrounded to high resistance grounding. We also added pulsing technology so that they can easily locate faults, and this HRG upgrade maintained process continuity and improved safety. Pulsing technology allowed them to quickly locate faults. Equipment damage and operational risks were significantly reduced, and the solution aligned with IEEE standards and proved cost effective. So the benefits that were apparent from ungrounded to HRG was the ability to easily locate ground faults, because you couldn't do that before in an ungrounded system, and also to control the transient overvoltage condition, that of which plagues the ungrounded system. And that is all for this presentation. If you have any questions, feel free to ask in the questions pane, and we'll go over those right now. So for the difference between high resistance and low resistance, that's actually going to be covered in our next session, which is next week, Tuesday. For the sizing of the NGR, we're also covering that next week, Tuesday, for the second session that we're going to be doing. These questions will be, all of these questions that are being asked right now are going to be covered in our next session for the selection and installation of the NGR, as well as the differentiation of when you should use high resistance grounding and low resistance grounding. So please sign up for that session, and all of your questions will be answered during that session. So the purpose of this session was essentially to address the different system grounding configurations that we typically utilize. And in the next sessions, we'll go a bit more in depth on the selection and installation of the NGR. Now, Vikranth, you asked, can you explain HRG causing the increase in arc flash? Well, it has to do with the fact that the voltage from line to ground on the unfaulted phases is increasing, and that's what causes the arc flash hazard to increase since voltage is increasing. But with coordination and proper design, it will be a safe solution and reduce risk. How can you locate the fault location using zero sequence CT? Can you explain the theory behind it? So there will be an unbalance of current as the ground fault current is flowing back to the point of fault. So the path that the ground fault takes is essentially going to ground, and then it goes up through the resistor point, and after it gets to the neutral, it goes to the faulted phase and back to the point of fault. So if a zero sequence CT is placed at a feeder and the feeder is experiencing a fault, that zero sequence CT is picking up that imbalance of current that's routing back to the point of fault from the source. What will happen if there are multiple ground faults? How does pulsing work then? Well, the pulse will basically split up based on the ground faults that are occurring, but you try and go for the one that is giving you the biggest swing and reading, and that's the one that usually you would go to trace out and then try and find. For lower level faults, you would work downward from there. So try and address the ones that are moving back and forth with a high level of magnitude, and then look at the ones which have minimal back and forth movement to address those smaller faults after. Does this pulsing have negative impacts on the motor asset? We have had no issues with pulsing impacting motor assets because it's a very small pulsing impact. Usually what we do for our Omni resistors is pulse down from 5 amps to 2.5 amps and not increase the ground fault current by pulsing up. So we've standardized on pulsing down to reduce the likelihood of additional damage to equipment. Even pulsing up will not necessarily do that, but some people may think so. It's opinion based pretty much here. Do power study reports describe when neutral grounding resistors are required to limit to ground fault current? So Robert, I'm not sure if it requires to limit ground fault current, but it is a method to limit ground fault current to prevent equipment damage. When should we use high resistance grounding? What tools should we use to make this determination? An ideal candidate for high resistance grounding would be applications that are mission and critical, like industrial applications, whether that be mining, oil and gas, wastewater treatment, hospitals, data centers, critical food processing, or anything that cannot tolerate tripping on a first fault condition. If your system is 3-phase 3-wire and not satisfying single phase loads, then it is an ideal candidate for high resistance grounding because you're not distributing the neutral. And if you have a Y transformer, then you would just connect the resistor from the neutral point to ground to make that high resistance grounded. If you're delta fed, then you would implement a zigzag transformer to establish an artificial neutral and place a resistor between that artificial neutral to ground. And we can also supply those zigzag transformers. Why was the zigzag required for case study 2? So for case study 2, their system was delta fed because they were coming from an ungrounded system. And so in order to establish a neutral to connect the resistor to basically create a return path for fault current, a zigzag was required since we couldn't place the resistor at the delta since there was no area to connect it to there. What are the benefits of a zigzag grounding transformer versus using an HRG? That comes down to the configuration of what you have at the secondary of your transformer. If you're Y configured and there's a neutral available, then you would just place the resistor between that neutral point to ground. If you have a delta configured system, again, the benefit would be to just establish a neutral with the zigzag and then place a resistor between that established neutral and ground to convert the resistance grounded. Is there a rule of thumb to conservatively estimate the system charging current based on MVA available on the systems to size the NGR? There is, and we have that in our consultant specification guide. What will happen to the contactor when pulsing? Shouldn't that contactor is damaged by the high current? The contactor is rated for the current, so it won't get damaged by the high current. We're using a 12-volt DC signal coming from our relay to pulse that contactor, and the contactor is suitably rated for the conditions. I've heard many times that single line to ground faults are over 90% of the faults. I believe this statistic includes outdoor distribution, where a very high percentage are single line to ground faults due to a lightning or foliage. Do you have a single line ground statistic just for industrial indoor distribution? I can check to see if we have anything like that. I was not aware that the majority of the statistic was from outdoor applications involving outdoor distribution. So I'll look into that and see if I can provide a response. What I do know is based on the applications that we've been involved in for oil and gas and pulp and paper, there are single line to ground faults occurring on much older facilities, and that high resistance grounding has been helping them basically locate these faults and address them accordingly without interrupting their process. Would you use an NGR on a generator? Any concerns or recommendation? So IEEE and NEMA standards recommend grounding the generator via resistance grounding. In general, generators have a very good tolerance on a 3-phase fault, but when it comes to a single line to ground fault, there's high levels of fault current that can occur and that can damage the generator. So typically generator manufacturers reach out to us to provide resistance grounding as part of their package that they submit to the consultant. So a lot of generators in North America are resistance grounded, and our top customers are generator manufacturers as well. So there's a very good good recommendation to utilize NGRs on generators. My suggestion, Alex, would be to also look at your stator core earth fault damage curves that you would get from the generator manufacturer and try to stay within the areas of acceptable damage and stay away from the areas which would cause critical damage. Is this pulsing option standard or optional? We can provide non-pulsing or pulsing. For low voltage systems, pulsing is pretty inexpensive, so we can provide it as a standard. On our NGRs, we have it as a standard because pulsing is a great way to locate faults manually. But if the customer doesn't want it, or he believes that he's going to be tripping on first fault, then he or she does not need to implement that. And we will build in accordance to what you specify. So at the end of the day, it's based on your decision. We can only outline the benefits of pulsing, but if it's not needed, then we can also build non-pulsing. Can you speak to the increased insulation of the power cables required for HRG systems? So in IEEE 242 Chapter 9, they have insulation levels for cabling to hold the fault for longer than 1 hour. In order to hold the fault for longer than 1 hour, the cable needs to be having an insulation level of 173%. In this case, that will allow you to hold the fault indefinitely. 133% rating, I believe, gets you up to 1 hour. And I think the standard 100% was a minute. I'm not sure off the top of my head. But look at IEEE 242 Chapter 9. There's a table there that will outline that. Or if you have a copy of the NEC, there's also some stipulations there with respect to cable insulation levels. I got a note from ElectroFed Canada indicating that for 480 and 600 volt cables, there's already enough mechanical insulation to suffice the electrical insulation of 173%. But in low voltage systems, most people just use 1 kV rated cable to suffice the requirement. Is it common practice to set NGR tripping at 50% of its rating? It really depends on the preference of the customer. We offer a range between 5 to 50%. And let's say on a 5 amp NGR, my approach would be to set at 20%. So picking up on 1 amp just to see, like, get that early warning in on a 20% fault just to see, if we can locate it or see where it's coming from before we even get to that 50% case. Some people want even more sensitivity than that and they choose to go with 5%, but then, not sure if that's even a high enough value to go out there and address it. So usually my recommendation is go with like in the range of 20-25%, but that's just my personal preference. Everyone is different and we have the range between 5 to 50%. So in an older industrial distribution system, it makes sense that a fairly high percentage of ground faults are single line to ground due to insulation breakdown. Yeah, I agree with that, John. Yeah, basically as the system begins to degrade and wear, we're going to see insulation being impacted. In addition to that, if voltage levels have been high or if there's been any spiking or transient over voltages from switching, there's a possibility that insulation gets punctured every time there's an over voltage incident. So in lieu of that, there are more indoor based ground faults, single line to ground faults occurring from the phase to ground in these applications as the system ages, for sure. Sergio has an excellent paper on generator grounding, especially when multiple generators are in parallel. We do have that paper available. We are also going to be doing an expert session on that, I believe. So stay tuned for that in terms of getting the information on that. Besides the long feeder cable runs, what other elements do you consider when calculating charging current? The major contributors are obviously the cable runs, but we also have to look out for surge capacitor sets. Inherently, transformers, motors, and generators have a very low capacitive charging current, but they're still accounted for. Okay, I think that is the last question. Thank you all for attending this session and look forward to seeing you guys again on the next one, which is happening next Tuesday. We also have the 1 p.m. session, which is going to be a repeat of this one. And thank you again for coming. Really appreciate your attendance. Thank you.